All right. Hello, everyone, and welcome to the fourth in this series of lectures, series of public talks, where tonight we are going to talk about motion, energy, and gravity, all things very important and to understand astronomy, to understand the universe. Essentially, we're going to be covering a Physics 101 class today, all in one video. Um, and any Physics 101 basic level mechanics class is all about pretty much one guy, Isaac Newton. And that, at a quote of his, is what we will start tonight with. If I have seen farther than others, it is because I have stood on the shoulders of giants. So the way we talk about motion in our everyday lives is very good. We communicate a lot of information the way we talk about motion, but scientists have more particular definitions of some of the terms that we use commonly. And so that's what we're going to start off tonight with is getting those scientific definitions down. Sounds boring, but I have really pumped this talk full of animations to hopefully make it go easier. So we'll start with speed, velocity, and acceleration. So speed tells us how far something will go in a certain amount of time. So we might say something like 100 kilometers per hour. I guess Americans wouldn't say that. We'd say something like 60 miles per hour. But 100 kilometers per hour is a speed. Velocity attaches a direction to that speed. So we would say something like 100 kilometers per hour north, or 60 miles per hour towards Atlanta, something like that. That is a velocity. An acceleration is a change in that velocity in any way, either in speed or direction or both. So note that we normally think of acceleration as increasing in speed, but technically slowing down is an acceleration. We tend to just call that deceleration, but that's an acceleration. If you're going at a constant speed around a curve, that is also an acceleration because you're constantly changing direction. So all three of these cars will be accelerating in some way. The first car is going to speed up. The second car is going to turn at a constant speed. And the third car is going to slow down. All of that was some form of acceleration. You've experienced that in your everyday life when you are sitting in a car driving or as a passenger. As the car speeds up, you feel yourself being pushed back. As the car slows down, you feel yourself being pulled forward. And as you go around a bend in the road, you feel yourself being pushed in the opposite direction to what you're turning. That's all acceleration. In contrast, if you're traveling at a constant velocity, you're not accelerating, you wouldn't feel any of that. Which is why, as long as an airplane isn't going through too much turbulence, that's why you don't feel motion on an airplane, because it's not accelerating. The velocity isn't changing. One of the most important accelerations in physics and astronomy is the acceleration of gravity. That's the acceleration of a falling object. So you've probably heard the famous story of Galileo dropping various objects off of the Leaning Tower of Pisa. And he was the one who deduced that gravity accelerates all objects by the same amount, regardless of the mass of the object. Now, intuitively, that doesn't really make sense because obviously, like a feather just kind of floats to the ground. Meanwhile, you drop a bowling ball, and that's just going to immediately sink. The difference there is air resistance. If you were to go to the moon, where there's very little atmosphere, and I believe one of the Apollo 16 or 17 astronauts did this. You can actually find the video of it on YouTube. I've used it in other presentations before. They dropped a feather and a hammer, and they fell at the same rate, hit the ground at the same time. That's the acceleration of gravity. On Earth, we can measure the acceleration of gravity. We measure the acceleration of gravity on any object, but on Earth, that's the one that's important. The acceleration of gravity causes falling objects to fall faster by 9.8 meters per second with each passing second. Or in other words, the acceleration of gravity, which we abbreviate as little g, is 9.8 meters per second squared. So this animation here on the right, which I'll press play on in a moment, shows the position of a ball. If you were on top of a 100-meter high building and you threw the ball with a velocity of 5 meters per second away from the building with no vertical velocity, just a horizontal velocity, gravity will do all the changing on the vertical direction. So as I press play, you'll see that the ball speeds up as time increases. So at a time of 1 second, it's moving at 10 meters per second down, 2 seconds, 20 meters per second down, 3 seconds, 30 meters per second down, and so on and so forth. Obviously, it's going to hit the ground at some point, so it will stop moving. But that's essentially how the acceleration of gravity works. A very, very important thing to understand for things happening on Earth. So the concepts of speed, acceleration, and velocity talk about what happens to individual objects, but all the interesting stuff in the universe is about interacting systems. So we need two additional concepts to describe those interactions, and that is momentum and force. So momentum is the product of an object's mass and velocity. If you're in a physics class, you would need to know this formula. You don't need to know this formula. Just know that we write momentum as P. Why it is symbolized by P, don't ask. I have no idea. We just use P. Is equal to mass times velocity, m times v. And then the only way to change an object's momentum is to apply a force to it. So we can understand these concepts by thinking about collisions. So imagine you are stopped in your blue car at a red light, and a bug, a fly, is flying towards you at a velocity of 30 kilometers per hour, and it slams into your windshield. Well, obviously, nothing much happens to you except for a bit of mess on the windshield. But now imagine that a 2-ton truck runs the red light and slams head on with you. Now, obviously, that truck is going to cause far more damage. I don't know if your car is going to spontaneously ignite, but it could. And we can understand why by considering momentum and force in each collision. So before the collisions, the truck's much greater mass means it has way more momentum than the bug, even though both the truck and the bug are moving with the same speed. During the collisions, the bug and the truck each give your car some of their momentum. The bug doesn't have a lot of momentum to give. Remember, it doesn't weigh very much. It doesn't have as much mass. Meanwhile, the truck has a lot of momentum to impart to your car, and that has the drastic effect of damaging yourself and your car. But note that the mere presence of a force does not always cause a change in momentum. So, for example, a moving car is always affected by the forces of air resistance and friction with the road. Forces that will slow your car if you take your foot off the gas pedal. But you can maintain your speed and hence constant momentum if you step on the gas pedal hard enough to overcome the forces of air resistance and friction. In fact, forces are always sort of present, like the force of gravity or the electromagnetic forces between atoms in your body. So we like to talk of forces in terms of the net force. The net force acting on an object represents the combined effect of all the forces put together. So there is no net force on your car when you're driving at constant velocity because the force generated by the engine to turn the wheels precisely offsets the forces of air resistance and friction. A change in momentum occurs only when the net force is not zero. And then changing an object's momentum means changing its velocity as long as its mass remains constant. So a net force that is not zero, therefore, causes an object to accelerate. And conversely, when an object accelerates, a net force must be causing the acceleration. We can use this kind of idea to understand many astronomical processes. So for example, planets are always accelerating as they orbit the sun because their direction of travel is constantly changing as they go around in their elliptical orbits. We can therefore conclude that there must be some force causing this change in acceleration. And as we'll discuss in a moment, Isaac Newton identified that force as gravity. But speaking of planets obviously don't travel in straight lines. They travel in circles. So there are some extra terms when we start talking about circular motion. So think of an ice skater. on spinning in place. Obviously, she's not going anywhere. She's spinning in place. So she doesn't have any overall velocity and hence no overall momentum. But every part of her body is moving in a circle as she spins. So those parts have momentum, even though her overall momentum is zero. Because remember, she's not going anywhere. So just doesn't have an overall momentum. So the way we would talk about this particular situation is that her spinning gives her angular momentum, which you can think of as turning momentum. Any object that is either spinning or moving along a curved path has angular momentum. So for example, this figure shows that the Earth moving along its orbit has orbital angular momentum. And then as the Earth spins on its axis, it has rotational angular momentum. And because angular momentum is a special type of momentum, an object's angular momentum can change only when a special type of force is applied to it. And we call that special type of force a torque, which you can think of as a twisting force. So to understand how torques work, imagine you are pushing on a door. Now, obviously, if you want the door to open, you don't want to be pushing on the hinge directly. That's not going to do anything for the door. But as you move further away from the hinge, you're able to cause the door to move with less and less torque. You'd have to push really, really hard near the hinges to get the door to open. And similarly, you don't really want to push like they show in part D of this figure. You don't want to push on the side of the door to get it to open. That's not going to do anything. You're going to be wasting some energy there. So we can see here in this little example that the amount of torque depends not only on how much force is applied, but also on where it is applied. Changing a tire, if you ever had the unfortunate need to change your tire yourself, that kind of offers another example of a torque. So turning the bolts on a tire means making them rotate, which requires giving them some angular momentum. A longer wrench means you can push from farther out than you can with a short wrench, so you can turn the bolts with less force. So we'll see many applications of angular momentum and torque throughout astronomy, because everything is spinning or orbiting around something. We'll see angular momentum pop up a lot all over the place. One of the final things I want to kind of clarify from what we commonly think of, is the difference between mass and weight. Now on Earth, the difference does not matter at all. But it is very important in astronomy where we're talking about things other than on Earth. So your mass is the amount of matter in something, say your body, but your weight is the force that a scale measures when you stand on it. Therefore, weight depends both on your mass and on the forces acting on your mass. So to understand the difference between mass and weight, let's imagine you have a scale in an elevator. Now, if you're like me, a student at Furman University, and taking General Physics 111, when we get to this part of the class, they would actually have put a scale in a nearby elevator that you can try out in between classes. And I did. This does actually work. If you have an elevator nearby that you can use, bring a scale in and actually see this in action rather than just relying on me telling you that this works. This is something you can go out and do. You can try it at home. So, so your mass in this elevator, your mass will be the same no matter how the elevator moves, but your weight will vary. So when the elevator is stationary or moving at a constant velocity, your weight would be your normal weight. When the elevator accelerates upward, you would feel the floor exerts a greater force than it does when you're at rest. You would feel heavier, and the scale verifies your heavier weight. When the elevator accelerates downward, the floor and the scale exert a weaker force on you, so the scale registers less weight. So note that the scale only shows a weight different from your normal weight only when the elevator is accelerating, not when it is going up and down at a constant speed. So therefore, your mass depends only on the amount of matter in your body and is the same anywhere, but your weight can vary because the forces acting on you can vary. So for example, your mass will be the same whether you're on Earth or the moon, but your weight will be different on the moon because of the moon's weaker gravity. Now, let's consider what happens, especially for this unfortunate person in this elevator, if the elevator cable breaks. Now, the elevator and you are in free fall, falling without any resistance to slow you down. The floor drops away the same rate that you fall, allowing you to float freely above it. And the scale reads 0 because you're no longer held to it. In other words, your free fall has made you weightless. Now, you don't have to be in the unfortunate situation of being trapped in an elevator when the cable snaps to experience weightlessness. You're in free fall whenever there's nothing to prevent you from falling. So just jumping off your chair or jumping up and down on a trampoline. When you're at that height, when you're at the tallest point of your trajectory, you're in free fall. You will feel weightless. Though your weightlessness will only last for a few seconds until you touch down on the ground. Now, you've probably seen astronauts in the International Space Station floating around, and many people would incorrectly guess that there's no gravity in space. But obviously, that's not true, because if there was no gravity in space, then there was nothing holding the International Space Station in orbit around the Earth. Astronauts appear like they're floating for the same reason that you are weightless when you jump off a chair. They are in free fall. Astronauts are weightless the entire time they orbit Earth because they are in a constant state of free fall. So to understand this idea, this is actually a thought experiment that Isaac Newton did back in the 1600s. Let's imagine a tower that reaches all the way up to the height of the space station's orbit, about 350 kilometers up. If you were to just step off the tower, obviously you're just going to fall straight down, remaining weightless until that unfortunate time when you do hit the ground and splat all over the Earth. But now imagine instead of just stepping off, you get a running start. Obviously, you're still going to hit the ground, but because of your forward motion, you will hit the ground a little bit, a short distance away from the base of the tower. The faster you run out of the tower, the farther you go before landing. So if you somehow were able to run as fast as the International Space Station, which is about 28,000 kilometers per hour, or about 17,000 miles per hour, a very interesting thing would happen. Oh, excuse me. By the time gravity had pulled you downward as far as the length of the tower, excuse me again, you'd already have moved far enough around the Earth that you'd no longer be going down at all. Instead, you'd be just as high above Earth as you've been all along, but a good portion of the way around the world. In other words, you'd be orbiting Earth. The space station and all other orbiting objects stay in orbit because they are constantly falling around the Earth. Their constant state of free fall makes these spacecraft and everything in them weightless. So now you might imagine that the complexity of motion in daily life means that the laws of physics that govern motion are going to be very complex. But they aren't really. In fact, it just took one man in the 1600s to write down those laws of motion. And that man is, of course, the man, the myth, the legend, Isaac Newton. So Newton, a little bit of history for you. Newton was born in Lincolnshire, England on Christmas Day in 1642. His father was a farmer who never learned how to read and write and died about 3 months before Newton was born. Newton had a difficult childhood and he didn't really show any signs of unusual talent. He attended Trinity College at Cambridge, where he earned his keep by performing menial labor, such as cleaning the boots and bathrooms of wealthier students and waiting on their tables. When the plague, not the current one, but the historical one, when the plague hit Cambridge shortly after Newton graduated, he returned home. By his own account, he experienced a moment of inspiration in 1666 when he watched an apple fall to the ground. And he suddenly realized that the gravity making the apple fall was the same force that held the moon in orbit around the Earth. In that moment, Newton shattered the remaining vestiges of the Aristotelian view of the world, which for centuries have been accepted as unquestioned truth. Aristotle had made many claims about the physics of motion, using his ideas to support his belief in an Earth-centered universe. He'd also maintained that the heavens were completely distinct from the Earth, so that physical laws on Earth did not apply to the heavens. By the time Newton saw the apple fall, the Copernican revolution, which we talked about last week, had displaced Earth from a central position, and Galileo's experiments had shown that the laws of physics were not what Aristotle had believed. So Newton's sudden insight delivered that final blow to Aristotle. By recognizing that gravity operates in the heavens as well as on Earth, Newton eliminated Aristotle's distinction between the two realms and brought the heavens and Earth together as one universe. This insight also heralded the beginning of what I do, astrophysics, although people didn't start calling it astrophysics until many centuries later. But astrophysics applies the physical laws discovered on Earth to the rest of the universe. And so over the next 20 years, Newton completely revolutionized mathematics and science. He quantified the laws of motion and gravity, conducted crucial experiments regarding the nature of light. He built the first reflecting telescopes, and he invented the mathematics of calculus. The compendium of Newton's discoveries is so tremendous that it would actually just take a solid book to go through all of them, and it would take several more books to describe their influence on civilization. And when Newton died in 1727 at the age of 84, the English poet Alexander Pope composed the following epitaph. Nature and nature's laws lay hid in the night. God said, let Newton be, and all was light. So now let's get into his three laws, which he published in 1687 in his book, Philosophiae Naturalis Principia Mathematica, which is Latin for Mathematical Principles of Natural Philosophy, but we usually just call it the Principia. And he enumerated three laws that apply to all motion, both here on Earth and in the cosmos. And so we'll walk through these laws. Newton's first law states that an object moves at constant velocity if there is no net force acting upon it. In other words, objects at rest stay at rest, and objects in motion stay in motion unless acted upon by an outside force. This is just essentially restating what Galileo had already previously shown, but it really codified it. So you've experienced this motion all the time. You know that a car just parked in a parking lot is not going to suddenly start moving of its own volition. Similarly, a car moving at a constant velocity shouldn't slow down, but it does. So that means there must be some force acting upon it. And of course, we've already mentioned those forces, air resistance and friction. That means if you were to put a car into space, like Elon Musk has, then that car will continue moving at the same speed forever, although the force of gravity will eventually change its direction and acceleration. So that's why interplanetary spacecraft like New Horizons or the Voyager missions, Juno, all of our spacecraft don't require any extra fuel once they're launched into space. And that's why astronomical objects like Earth, Mars, the sun, the galaxy don't require any extra force to just move throughout the universe. There is no force acting on them. And this first law also explains why you feel no motion when you're walking around, when you're traveling on a plane, on a smooth flight, as long as there's no turbulence. Because as long as the plane is traveling at a constant velocity, no net force is acting upon it or you in the plane. There you go. That's the scientific explanation for why you don't even realize you're moving when you're on a plane, except for the obvious fact when you look out a window and see the clouds going by. Newton's second law states that force is equal to mass times acceleration, famously just F equals ma, or alternatively, force is the rate of change in momentum. So this law explains why it's easier to throw a lightweight object than a heavier object. So say you're going to throw, trying to throw a baseball and a bowling ball. Now, because the baseball has less mass, the same force from your arm will impart a greater acceleration to the baseball than the bowling ball. And therefore, the baseball will travel further than the bowling ball. Astronomically, this Newton's second law explains why a large planet like Jupiter will have a much greater effect on the asteroids and comets than a small planet such as Earth. Because Jupiter is much more massive than Earth, it will exert a stronger gravitational force on passing asteroids and comets, and therefore sends them scattering with a greater acceleration. This law also explains acceleration around curves. So if you look at this, just high res figure, You see this man twirling a ball around on a string. Now, obviously, the ball is accelerating, constantly changing direction. He may be keeping it going at the same revolutions per minute, but it is accelerating because it's constantly changing directions. And since that ball is accelerating, that string must be applying an inwards force to keep the ball in. If the string were to break, as you see on the right half of the figure, that ball is going to zoom off with a constant velocity from the point of break because there's no longer a force acting on it to cause it to accelerate. So that also explains why planets are accelerating in their circles. Planets orbiting the sun always have an acceleration in the direction of the sun, and gravity is that inward force causing that acceleration. And in fact, it was this kind of discovery that gravity is that force that allowed Newton to then uncover his law of gravity, which we'll talk about in a hot moment. And then finally, Newton's third law says that for any force, there's an equal and opposite reaction force. So let's think about this one for a moment. So think about standing still on the ground, just standing up. Your weight will exert a downward force. So if this force were acting alone, Newton's second law would demand that you accelerate downwards. The fact that you're not falling when you're standing means that there must be a net force acting on you, which is only possible if the ground is exerting an equal and opposite force. So in other words, an upward force on you that precisely offsets the downward force you exert on the ground. The fact that the downward force you exert on the ground is offset by an equal and opposite force that pushes upward on you is Newton's third law of motion. And it's very important in astronomy because it tells us that objects always attract each other through gravity. So for example, your body exerts a gravitational force on Earth, identical to the force Earth exerts on you, except it acts in the opposite direction. Of course, the same force means a much greater acceleration for you than Earth because you have less mass than the Earth, which is why you fall towards the Earth rather than the Earth falling towards you. Newton's third law also explains how a rocket works. So a rocket engine generates a force that drives hot gas out the back, which creates an equal and opposite force that propels the rocket forward. So now let's talk about some conservation laws. So Newton's laws of motion are kind of easy to state, but they do seem a bit arbitrary. Is there some deeper fundamental truth? For example, why should every force be opposed by an equal and opposite reaction force? And in the century since Newton, we have learned that these laws reflect deeper aspects of nature known as conservation laws. So let's investigate the most important of them for astronomy. And the first one is the law of conservation of momentum. And that states that as long as there is no external forces, the total momentum of interacting objects cannot change. In other words, their total momentum is conserved. So an individual object can gain or lose momentum only if some other object's momentum changes by the precisely opposite amount. So let's investigate this by imagining a game of pool. So Newton's second law tells us that when one pool ball strikes another, it exerts a force that changes the momentum of the second ball. At the same time, Newton's third law tells us that the second ball exerts an equal and opposite force on the first one, which means that the first ball's momentum changes by precisely the same amount as the second ball's momentum, but in the opposite direction. The total combined momentum of the two balls remains the same both before and after the collision. So here are our two balls. We've got a green one and a blue one. The green one is moving towards the right with the momentum, mass times velocity. The blue ball is stationary. It hasn't moved at all. And so it has a momentum of 0. Now, as the green ball comes in, it's going to hit that ball, and momentum is going to be transferred from the green ball to the blue ball. And the blue ball will now have a momentum of m times v, and the green ball will be stationary. It'll have a momentum of 0. So from the perspective of conservation of momentum, Newton's first law makes perfect sense. When there is no net force on an object, there is no way for the object to transfer any momentum to or from any other object. It remains at rest. So conservation of momentum is an absolute law that always holds true. For example, it holds even when you jump up into the air. You may wonder, well, where do I get the momentum that carries me upward? The answer is that as your legs propel you skyward, they're actually pushing Earth in the other direction, giving Earth's momentum an equal and opposite kick. However, Earth's huge mass renders its acceleration undetectable. And during your brief flight, the gravitational force between you and Earth pulls you back down, transferring your momentum back to Earth. And so the total momentum of you and Earth remains the same at all times. So now, perhaps you have wondered how Earth manages to keep rotating and going around the sun day after day and year after year. And the answer lies in our second conservation law, the law of conservation of angular momentum. So this one states that as long as there is no external torque, the total angular momentum of a set of interacting objects does not change. So there are two different types of angular momentum. I mentioned them briefly before, and we'll go through both of them individually. So consider orbital angular momentum. So look at Earth's orbit, where a simple formula tells us that the angular momentum is equal to the mass of Earth times the orbital velocity, v, times the radius of the orbit, r. Because there are no objects around to give or take angular momentum from Earth as it orbits the sun, Earth's orbital angular momentum must always stay the same. This explains two key facts. So Earth needs no fuel or push of any kind to keep orbiting the sun. It will keep orbiting as long as nothing comes to take its angular momentum away. And because Earth's angular momentum at any point in its orbit depends on the product of its speed and orbital radius, Earth's orbital speed must be faster when it's nearer to the sun and slower when it's farther away from the sun. In other words, the law of conservation of angular momentum tells us why Kepler's second law is true. So Kepler stumbled upon an absolute truth about the universe. He just didn't know that it was an absolute truth. The other type of angular momentum is rotational angular momentum. So the same idea explains why Earth keeps rotating. As long as Earth isn't transferring any of the angular momentum of its rotation to another object, it keeps rotating at the same rate. Now, technically, the Earth is transferring some of its rotational angular momentum to the moon. And so the Earth's rotation is gradually slowing down. We'll talk about that towards the end of tonight. But this also explains why we see so many spinning disks in the universe, such as the disk of galaxies like the Milky Way and disks of material orbiting young stars, because it's all about this conservation of angular momentum. Next, we're going to talk about energy. And so we have the law of conservation of energy that tells us, like momentum and angular momentum, energy cannot appear out of nowhere or disappear into nothingness. Objects gain or lose energy only by exchanging energy with other objects. So we'll see numerous examples through which we can understand astronomical processes simply by studying how energy is transformed and exchanged. But before we can really fully understand the law of conservation of energy, we've got to talk about the different types of energy. We need to know what energy is. In essence, energy is what makes matter move. And because that statement is really broad, we'll talk about the different types of energy. So we have kinetic energy, which is the energy of motion. So falling rocks, orbiting planets, and the molecules moving in the air are all examples of objects with kinetic energy. Quantitatively, we write this as 1/2 times the mass of the object times the velocity of the object squared. The energy carried by light is called radiative energy. All light carries energy, which is why light can cause changes in matter. So for example, light can alter molecules in our eyes, allowing us to see, or warm the surface of a planet. And then stored energy is potential energy, which might later be converted into kinetic or radiative energy. So for example, a rock perched on a ledge has gravitational potential energy because if it falls, it will because it will fall if it slips off the edge. And gasoline contains chemical potential energy that can be converted into the kinetic energy of moving a car. Regardless of what type of energy we're talking about, we can measure how much, we can measure the amount of energy with the same standard unit. So Americans are more familiar with calories, which are in food, but the scientific unit is called a joule. The abbreviation is a capital J. And so you can see here in this table, I've compiled a bunch of energies and how many joules they are. So the energy of sunlight at Earth is about 1,300 joules. The energy of metabolism from a candy bar is about 1,000,000 joules, which is the same amount of energy as a car going 60 miles per hour. The energy released by a 1 megaton H-bomb is about 4 times 10 to the 15 joules. The energy released by a supernova, truly just astronomical thing, is 10 to the 44 or between 10 to the 44 and 10 to the 46. Remember, that's 1 with either 44 or 46 zeros after it. And although there are these kind of 3 major types of energy, we'll sometimes divide them into various subcategories. So in astronomy, the most important subcategory of kinetic energy is thermal energy, which is the collective kinetic energy of many individual particles moving randomly in a substance, like rock or the air or the gas within a distant star. In such cases, it's really much easier to talk about the thermal energy of the object rather than the individual kinetic energies of all of the random moving parts. And note that all objects contain thermal energy, even if they are still, since particles are always jiggling randomly. Thermal energy does get its name because it's related to temperature, but temperature and thermal energy are not the same. Thermal energy measures the total kinetic energy, while temperature measures the average kinetic energy. So thermal energy does depend on temperature, but also on the number and density of the particles. So you can get a feel for that by imagining that you could quickly thrust your arm in and out of a hot oven and a pot of boiling water. Now, the air in a hot oven is going to be much hotter than a pot of boiling water, but you'll notice that it doesn't hurt to put your hand in an oven briefly. The reason for that difference is because of density. In both cases, because the air or water is hotter than your body, the molecules striking your skin will transfer thermal energies to the molecules in your arm. The higher temperature in the oven means that the air molecules are striking your skin harder on average than the molecules in the boiling water. But because the density of the water is so much higher than the density of air, many more molecules strike your skin each second in the water. The sheer number of molecules hitting you in the water means that more thermal energy is transferred to your arm. That's why boiling water, putting your hand in a pot of boiling water will cause a burn almost instantly, while as putting it in an oven just briefly, you won't even feel a thing. The environment in space provides another example of the difference between thermal energy and temperature. Surprisingly, the temperature in low Earth orbit can be several thousand degrees. However, astronauts working outside don't burn up in low Earth orbit despite the temperature because it's low density. So the thermal energy is low. The temperature can be high. All right, hopefully we understand the difference between temperature and thermal energy now. Now let's move on to potential energy. So gravitational potential energy depends on an object's mass and how far it can fall as a result of gravity. If you're near the Earth's surface, we just say it's the mass times the acceleration of gravity times the height above Earth's surface. So, for example, if you throw a ball up into the air, it has more potential energy when it's high up than when it's near the ground. Because energy must be conserved during the ball's flight, the ball's kinetic energy increases when its gravitational potential energy decreases, and vice versa. That's why the ball travels the fastest when it's closest to the ground, where it has the least gravitational potential energy. Another type of potential energy is something that was discovered by Einstein, and that is mass energy in his famous equation E equals mc squared. In other words, mass itself can be converted to energy, and energy converted into mass. So, for example, the energy released by a one megaton H bomb comes from converting only about a tenth of a kilogram of mass into energy. The sun generates energy by converting a tiny, tiny fraction of its mass into energy through a similar process called nuclear fusion. So now we've seen that energy comes in three basic categories: kinetic, radiative, and potential. And we've explored some subcategories. Now we're ready to return to the question of where objects get their energy. Because energy cannot be created or destroyed, objects always get their energy from other objects. Ultimately, we can always trace an object's energy back to the Big Bang. So, for example, imagine that you've thrown a baseball. It is moving, so it has kinetic energy. Where does kinetic energy come from? Well, the baseball got its kinetic energy from the motion of your arm as you threw it. Your arm, in turn, got its kinetic energy from the release of chemical potential energy stored in your muscle tissues. Your muscles got this energy from the chemical potential energy stored in the foods you ate. The energy stored in the foods came from sunlight, which plants convert into chemical potential energy through photosynthesis. The radiative energy of the sun was generated through the process of nuclear fusion, which releases some of the mass energy stored in the sun's supply of hydrogen. The mass energy stored in the hydrogen came from the birth of the universe in the Big Bang. So after you throw the ball, its kinetic energy will ultimately be transferred to the molecules in the air or the ground. So it may be difficult to trace after that point, but it will never completely disappear. This little animation shows the exchange between gravitational potential energy and kinetic energy. So on the left, you can see I've thrown an object, a ball, up in the air. On the right, you can see on the horizontal axis the time in seconds, on the vertical the energy in joules. And hopefully you can see sort of which lines indicate what thing. So remember, energy is conserved. So the flat purple line is the total energy in the system, about 45, 46 joules. The yellow line, notice that it's the highest when I've just thrown the ball and when the ball is landing. That is the kinetic energy. And then the green line, which follows the same path as follows the same shape as the ball's trajectory, is the gravitational potential energy, because it reaches its highest when the ball is at its highest. And notice that they mirror each other. That is the conservation of energy working. So here is a question. I create a little animation. This is Mars's actual orbit. And I want to know which quantities are conserved here. Is it position? Is it total energy, kinetic energy, potential energy? Is it its speed? Is it its angular momentum? There are multiple correct answers to this. So think about it, pause the video and think about it, and then unpause when you have an answer. All right. Yes, you can always tell a conserved quantity by looking for the straight lines. So the conserved quantities are the total energy and angular momentum. Obviously, the speed is changing throughout Mars's orbit. We know that from Kepler's second law. Position is obviously not conserved because it's going in an ellipse. And then potential and kinetic are changing as well throughout the orbit. Those aren't conserved as well. But total energy and I guess total angular momentum, I should have stated that, are the ones that are conserved. So we've now talked about Newton's laws of motion, and those describe how objects move in the universe in response to forces. The laws of conservation of momentum, angular momentum, and energy, often an alternative and often simpler way of thinking about what happens when a force causes some change in the motion of one or more objects. However, we cannot fully understand motion unless we also understand the forces that lead to the changes in the motion. So in astronomy, the most important of those forces is gravity, which essentially governs all large-scale motion in the universe. So Isaac Newton discovered the basic law that describes how gravity works, and he wrote them in 3 simple statements that can summarize this universal law of gravitation. First, every mass attracts every other mass through the force called gravity. We kind of knew that one already. The strength of the gravitational force attracting any 2 objects is directly proportional to the products of their masses. And the strength of gravity between two objects decreases with the square of the distance between their centers. In other words, gravity follows an inverse square law. Mathematically, we write the statement like this: the force of gravity, F subscript little g, is equal to big G times the mass of the first object times the mass of the second object divided by the distance between them squared. Here, big G as opposed to little g, which is the acceleration of gravity on Earth's surface. Big G is the gravitational constant, measured to be 6.67 times 10 to the minus 11 cubic meters per kilogram per square second. And that's the thing that we've measured. Just accept that measurement. Now, how does this law of gravity expand Kepler's law? So Kepler's law has been accepted as valid for nearly 70 years, but Newton removed any hint of doubt by showing why Kepler's laws were physically true. In particular, with the aid of the mathematics of calculus that he invented. So he showed why that the inverse square law of gravity leads naturally to elliptical orbits for planets orbiting the sun, which is Kepler's first law. As we've seen, Kepler's second law arises naturally from the conservation of angular momentum, and Kepler's third law arises from the fact that gravity weakens with distance from the sun. And Newton found that he could extend Kepler's laws into a more general set of rules about orbiting objects. So I've already just said these. And now let's get into these more general rules. So Kepler wrote his first two laws for planets orbiting the sun, but Newton showed that any object going around another object will obey those rules. So, for example, the orbits of a satellite around the Earth, or the moon around a planet, or an asteroid around the sun will all obey these rules. So he showed that ellipses are not the only possible shapes for orbits. Obviously, we've got circles and ellipses. These are called bound orbits, where an object goes around another object over and over again. But there are also unbound orbits, where an object comes close to another object just once, called a parabolic or a hyperbolic orbit. Together, these shapes, circles, ellipses, parabolas, and hyperbolas, are called conic sections to mathematicians, because you can imagine taking a cone and making different slices through the cone to get a circle, ellipse, parabola, or a hyperbola. Comets can move on parabolic orbits. We haven't found many things that actually had a hyperbolic orbit. They do exist, they just are rare. But parabolic orbits, comets, elliptical orbits, essentially anything that orbits the sun is an elliptical orbit. And just because an orbit may be unbound, doesn't change the fact that it will still obey all of Kepler's laws. They'll move faster when they're closer to the object they're orbiting, or slower when they're farther away. Still obeys Kepler's second law. We also usually think of one object orbiting another object, but Newton showed that the pair both orbit their common center of mass, the point at which the two objects would balance if they were somehow connected. So if you look at this figure, we have at the top, two stars of equal mass. The center of mass will lie halfway between them. Now, if we have one star that is twice as massive as the other, the center of mass will lie much closer to the more massive one. Then if you have a planet, which is just so tiny compared to the mass of a star, the center of mass will actually lie inside the star. So the star will still orbit the center of mass, will slightly wobble back and forth. We use this, this is a method we use to detect exoplanets around other stars. But it will appear as if the planet is just orbiting the star. In fact, it's orbiting the center of mass. Newton also found that Kepler's third law is a special case of a more general equation that allows us to calculate the mass of an object. So here's Newton's version. So we've still got a p squared equals a cubed, which is what we had in Kepler's third law, but we've got a bunch of other things. So we got a 4 pi squared, that's just some numbers. We've got big G, which is some numbers. And then the sum of the masses involved. Now, if you're talking about, say, the Earth going around the sun, things start to drop out. Now, obviously, the sun is way more massive compared to the Earth, so we'll just ignore one of those masses. Let's set G to be 4 pi squared. And then we do get p squared equals a cubed, as long as the period is measured in years and the distance is measured in astronomical units. So Kepler did a more simplified version, but Newton really showed us how to calculate masses. We still use this to calculate masses throughout the universe. It's the best way we know of to calculate masses. So now let's answer some questions about gravity, such as, how does gravity and energy help us understand orbits? So as a consequence of the law of conservation of energy, as long as no other object causes an object to lose or gain energy, its total orbital energy cannot change spontaneously, and its orbit will remain the same. But orbits can change through exchanges of energy, such as through gravitational encounters. So a comet on its own little elliptical orbit, if it passes, say, near Jupiter or Saturn or any of the massive planets, then it can exchange orbital energy with Jupiter and change its orbit to maybe a parabolic or different ellipse. Now, Jupiter doesn't change its orbit very much because it's massive. It's going to take way more energy to make Jupiter move. But they do exchange some energy there. Spacecraft engineers use that idea to in the reverse. So, for example, on its way to Pluto, the New Horizons spacecraft was deliberately sent past Jupiter on a path that allowed it to gain orbital energy at Jupiter's expense. Voyager 2, here's a nice little GIF. Voyager 2, you see the purple line is Voyager, and as it goes past each of these planets, it's stealing just a bit of those planets' orbital energy to change its own orbit. You watch it again as it goes past Mars, the green line. It will bend, and then Jupiter, the blue dot, really bending there, then Saturn, and then Uranus. Atmospheric drag, in other words, friction, although it's not really present in space, can cause objects to lose orbital energy, which will cause them to move into a lower orbit. So satellites in Earth's upper atmosphere have to expend a little bit of energy to stay in those orbits. Otherwise, some of that energy will go into the Earth's atmosphere, and the satellite will lose energy, causing it to drop lower and eventually crash back into Earth. Friction may also help explain why many outer planets have so many small moons. Those moons may have once orbited the sun independently, but the outer planets probably were once surrounded by clouds of gas, and friction would have slowed objects passing through this gas. Some of those small objects may eventually just lost enough energy to allow them to be captured as moons. So Mars is 2 moons, Phobos and Deimos, which we'll talk about in a few weeks, may have started orbiting Mars similarly. So far, gravitational encounters and friction causes things to lose orbital energy, but an object could gain orbital energy, will move into a higher orbit. And if it's given enough energy, it may end up reaching escape velocity, putting it into an unbound orbit. So the escape velocity from Earth's surface is about 40,000 kilometers per hour. And that's the minimum speed, the minimum velocity required to escape Earth's gravity for anything. It's independent of that object's mass. Whether it's an individual atom or molecule leaving Earth's upper atmosphere, or whether it's a rocket launching off from Cape Kennedy. It will have to reach at least 40,000 kilometers per second. All right, here is a multiple choice question for you. There is only one correct answer. So the Voyager spacecraft continues to speed out of the solar system, even though its rockets no longer have fuel. This is an example of Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Newton's law of gravity, or Kepler's second law. So pause the video, come back, see if you got it correct. If you answered first law of motion, you are correct. This is my attempt to trick you because we've just been talking about Newton's law of gravity. I want to see if you remember the laws of motion already. That's because, remember, no force is acting on it except for gravity a little bit. So we'll continue to if it's at a constant speed, it will continue to move at a constant speed unless a force acts on it to change it. All right, how does gravity cause tides? So, gravity attracts the moon and the Earth towards each other. That's Newton's third law in action. But it affects different parts of the Earth slightly differently, which you can see in the top right figure. So, the gravitational attraction to the moon is weakest on the side of the Earth furthest from the moon, slightly stronger at the center of the Earth, and then strongest at the side closest to the moon. That difference in gravitational attraction tries to pull the Earth apart, raising tidal bulges, both in the land and the water, but water is more movable than land. So that's why we just tend to talk about the water bulges. And it creates them both toward and away from the moon. That away from the moon is kind of confusing, but you can think of, obviously the moon is pulling on the nearest water bulge the hardest, but it's also pulling on the solid mass of Earth slightly, which even though it's pulling on the far side of the Earth the weakest, because the Earth has moved slightly towards the moon, we create a similar water bulge on the far side of the Earth. And it's Earth's rotation through these tidal bulges that creates the high and low tides twice each day. So a very famous example of the tides is at Mont Saint-Michel in France, where the tide rushes in faster than a person can swim. Before they built that bridge, at high tide, Mont Saint-Michel was an island twice a day. And people have sadly drowned when they've been caught as the tide rushes in. Yeah, the sun also exerts a tidal force on the Earth, but obviously it's way smaller compared to the strength of the moon, since the sun is way more distant from Earth than the moon. The overall tidal force caused by the sun is a little less than half that caused by the moon. And so when the tidal forces of the sun and moon work together at new and full moon, as this figure on the right illustrates, we get spring tides. The tides are a bit stronger at new and full moon. When the forces from the sun and moon counteract each other at the third and first quarter moon, we get weaker tides, which are called neap tides. You can see that here in this little GIF. So as the Earth rotates on its axis very rapidly, it's experiencing those high and low tides. But you can see as the moon changes its position in its orbit, those tides do get weaker and stronger as it aligns itself with the sun. So we get this whole combination of both the daily high and low tides, as well as the monthly spring and neap tides. Or I guess they're technically weekly. And so far we've talked about it as if Earth rotates smoothly through the tidal bulges, but because the tidal forces stretch Earth itself, that process creates friction, which we call tidal friction. So the moon tries to keep the tidal bulges on the Earth-Moon line, while the Earth wants the bulges to rotate along with it. And so there are two consequences. One, the moon will always pull back on the bulges, which will slow the Earth's rotation. And two, the bulges will pull back on the moon, adding orbital energy and letting the moon move further from the Earth. So these effects are barely noticeable on human timescales. So tidal friction increases the length of the day by only about 1 second every 50,000 years. But of course, they'll add up over the billion-year timescales that the solar system has existed. Early in Earth's history, a day may have only been 5 or 6 hours, and the moon may have been 1/10 or less its current distance from Earth. These changes also provide a great example of conservation of angular momentum and energy. The moon's growing orbit gains the angular momentum and energy that Earth loses as its rotation slows. This tidal friction is also what slowed the moon's rotation to its present state of synchronous rotation. Remember, we talked 2 weeks ago that the moon always keeps the same face towards the Earth. It's this tidal friction that caused that whole synchronous rotation. Probably long ago, the moon did rotate much faster than it does today. But eventually, that tidal friction slowed it. And tidal friction isn't just Earth and moon, it's anywhere. The Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, keep nearly the same face towards Jupiter at all times. And then Pluto and its moon Charon both rotate synchronously. Like two dancers, they always keep the same face towards each other. Some moons and planets exhibit variations on synchronous rotation. So Mercury rotates exactly 3 times for every 2 orbits of the sun. So this pattern ensures that Mercury's tidal bulge always aligns with the sun at perihelion, where the sun exerts its stronger forces. And finally, I want to answer the question of why do all objects fall at the same rate? So remember that Galileo discovered that the acceleration of a falling object is independent of its mass, but why is that? So if you drop a rock, the force acting on the rock is gravity. The 2 masses involved are the mass of the Earth, m-Earth, and the mass of the rock, m-Rock. If the rock isn't too far above the surface of the Earth, the distance is approximately the radius of the Earth, our Earth, so about 6,400 kilometers. So we would write it, here's on the left is just Newton's law of gravity. F is equal to big G times the mass of the Earth times the mass of the rock divided by the distance between the Earth and the rock squared. And like I just said, the distance is about Earth's radius, so the radius of the Earth squared. We remember Newton's second law, F equals ma. So set big G, m Earth, m rock over r Earth squared equal to ma. In this case, the m here is mass of the rock, and a is the acceleration of the rock. However, let's cross out things that are the same on each side. There's a mass of the rock on both sides. Those cross out. And so we now see that the acceleration of the rock, or any falling object, does not depend on that object's mass, only on the planet. So this shocked Newton and scientists for the next 240 years until Einstein discovered a deeper truth, which we will talk about much later on in the future. So that's one more down. It's motion, energy, and gravity. Next week, we'll talk about light and matter, very, very important for astronomy, and then how we observe that light and matter through telescopes, and then we'll finally get into the solar system. So thank you for joining me.